calculating bond order. So bond order has a formula. It is equal to the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. All divided by 2. And what bond order tells you, the higher the bond order, the stronger the bond. Also, if you get a bond order equal to 0, the molecule doesn't exist or cannot exist. That's a bold statement, but it's nonetheless true. And we'll do a calculation where we look at a molecule that doesn't exist. So if we look at into molecular nitrogen, we know that nitrogen has an electron configuration for 1s2, 2s2, 2p3. It has 7 total electrons, but we're interested in the valence electrons. So N2 has 10 valence. Sorry about that glitch. 10 valence electrons. So if we start filling in electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those 10 valence electrons, they fill up the orbitals. So we can calculate the bond order. So bond order BO we have 2, 4, 6, 8 electrons in bonding orbitals, lower energy orbitals. Bonding orbitals are lower in energy. 2, 4, 6, 8. Minus 2 electrons in an antibonding orbital. Divided by 2. 8 minus 2 is 6. 6 divided by 2 is 3. Nitrogen has a bond orbital of 3. Okay. And if you draw the Lewis structure of nitrogen, it has a triple bond. So a bond order of 3 is high. That corresponds to a strong bond, and molecular nitrogen has a triple bond. That's an example of how you calculate bond order. Bond order practice continued, and determining whether a diatomic molecule is paramagnetic or diamagnetic. So bond order, BO, is equal to number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. I'm just going to abbreviate anti, all divided by 2. So if we look at oxygen, molecular oxygen, O2, it has 12 valence electrons. And then, so 12. And we do our off-brow principle, build up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 valence electrons using our molecular orbital diagram, and plugging in from the formula, we can determine the bond order. We've got 2, 4, 6, 8 electrons in bonding orbitals. And there are going to be 4 in anti-bonding, divided by 2. 2, 3, 4 in anti-bonding. Those sum to 12. And our bond order is 2. So if you draw the Lewis structure of oxygen, you see that it's a double bond. If you draw that. So it's a strong bond, not as strong as nitrogen, as molecular nitrogen. It's a triple bond, but bond order of 2, a strong bond. Also, you see that there are 2 unpaired electrons here, and molecular oxygen is paramagnetic. If you pour liquid oxygen through a magnet, it is attracted by a magnetic field. Valence bond theory doesn't have a way to explain this, but molecular orbital theory does. Those unpaired electrons. Now, if you were to do the bond order of neon 2, that hypothetical molecule would have 16 valence electrons. And if you were to go and fill 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You would have an equal number of electrons in anti-bonding orbitals as bonding orbitals. 8 minus 8 would give you a bond order of 0. And that just confirms that neon 2, neon's a noble gas. It doesn't particularly bond with anything else. And N2, or dimolecular, or diatomic neon, doesn't exist. And molecular orbital theory helps confirm and explain that.